Welcome viewers to the first lecture for the online series of lectures for the course of Algebraic Topology 1. The course code for this course is MAT431. In this lecture we'll be discussing homotopy, path homotopy, and their various properties. Let us get started with the definition of homotopy. Given two continuous functions f prime from the topological space X to the topological space Y, we say that f is homotopic to f prime if there is a continuous function big F from the topological space X cross I to the topological space Y such that the following boundary conditions are met. F at x, 0 is equal to small f of x, and f at x, 1 is equal to small f prime of x for all small x in big X, where I is the closed interval from 0 to 1. Okay, here the topological space X cross I is equipped with the product topology. The map big F is called a homotopy between F and F prime. Okay, that F is homotopic to F prime is denoted by this. Okay, also if F is homotopic to F prime and F prime is a constant map, that is, there exists a y in big Y such that all of big X is going to be mapped to that single element of big Y under F prime. We say that small f is null homotopic. Okay, now we are going to define path in a topological space. Path. So before we considered a continuous function f from one topological space to another topological space Y. Now we will consider a specific situation where f is a continuous map from this closed interval to the topological space X. Okay, such that, so we consider this continuous function f from 0, 1 to x is continuous such that f at 0 is equal to x0, where x0 is a point in this topological space X, and f of 1 is equal to x1 belonging to the topological space X. So this point x0 is called the initial point of the path, and this point x1 in the topological space X is called the final point of the path. Okay, so a path in the topological space X is a continuous map from the closed interval 0, 1 to the topological space X such that f of 0 is equal to x0 and f of 1 is x1. x0 is called the initial point of the path and x1 is called the final point of the path. Okay, now if f and f prime are two paths in the topological space X, there is a stronger condition in other words, there is a stronger relation between these two paths, f and f prime, than mere homotopy. Okay, so this stronger relationship between the two paths is going to be defined now. So we have the second definition. Two paths f prime from the closed interval I to the topological space X are said to be path homotopic. This is the stronger relationship that we were referring to. Path homotopic if they have the same initial and final points, okay, and which we denote by x0 and x1 respectively, and if there is a continuous map, let me erase this top part. If there is a continuous map, a big F, from I cross I to X, such that four conditions are met. Big F of S, 0 is going to be equal to small f of S, and big F at S, 1 is equal to f prime of S. Big F at 0, t is the initial point x0, and big F at 1, t is the final point x1. And these four conditions are satisfied for all S and T in the closed interval 0, 1. We call F a path homotopy between F and F prime, a path homotopy between F and F prime. that f and f prime are path homotopic is denoted by this. Okay, so let me draw a picture for you. To explain path homotopy between two paths. So here we draw a square 0, 1 of length 1. Okay. So this is a square. On the x direction we have s, and in the y direction we have t. Okay. And there are two intermediate paths given by dots, and this is our I cross I, right? And f is taking us from this, the interior of the square to this topological space big X. So the initial point is x0 and the final point is x1. So let me first draw the two paths. This is f prime of s, and we draw f of s here. Okay, and these dots correspond to two paths. And this is the other dotted path. Okay, so this edge of this solid region corresponds to the path f prime. Okay, and this edge corresponding to a fixed t corresponds to this path in the topological space big X. Okay, all right. So this path corresponds to a fixed value of t taken to be 0, and for t to be 1 we have this path. Okay, but there are values between 0 and 1 of t, right? So we have chosen two fixed values of t here, and we have drawn the corresponding paths here. So we see that as we vary t from 0 to 1, we get a family of paths in big X. Okay, and this family varies continuously between the two paths fs and f prime s. So in this sense, f big F represents a continuous deformation of the path small f into the path f prime. Okay, all right. So we have a small remark here, which I already mentioned. Now, the first condition simply says that the first condition. Okay, so we had four conditions. Well, in fact, we had two conditions. So the first condition was f s comma 0 is equal to small f of s, and f s comma 1 equal to f prime of s. This is what we call the first condition now, and the second condition is f0 comma t is equal to the initial point, and f1 comma t is the final point x1. This is what we call the second condition. Okay. So the first condition tells us that these two paths are homotopic, small f and f prime. And the second condition puts restriction to the initial and the final points of these two paths. Okay? It tells us that the initial point of the two paths should be the same, and the final point of the two paths should also be the same. Okay, and in fact, the second condition tells us that we can construct a family of paths parameterized by t, which we denote by f twiddle sub t, and we define this family of paths by f twiddle sub t of s equal to big F of s comma t. Okay, and the two extremes of this family are f twiddle sub 0 s, which is just f of s, and f twiddle of sub 1 of s equal to f prime of s. Okay, good. Okay, now we state our first lemma of this lecture, lemma 1. Let me first state it and then I'll prove it. The relation sim and sim sub p. Okay, this is homotopy, this is path homotopy. These two relations are equivalence relations. This is the statement of the lemma. Okay, now if they are equivalence relations, then if f is a path, we will denote its path homotopy equivalence class by f within square bracket. Okay. Okay, so let me prove the statement. We'll prove it for homotopy. The proof for path homotopy is almost the same, so I'm not going to do it. I'll leave it as an exercise. Probably I'll just show the transitivity property of path homotopy. Okay, so we start with three continuous functions, f prime and f double prime, from the topological space X to the topological space Y. Proving f is Homotopic to itself is simple. We need to show that there exists a homotopy between from F to itself, and this homotopy, big F, from X cross I to Y is going to be defined by big F of X comma T is equal to F of X for all T in I. So if this is the case, then we immediately see that F of X comma 0 is equal to small f of X, which is equal to F of X 1, X comma 1. So we are done proving the reflexivity property of this relation. Now we have to prove symmetry. Let me erase everything. Suppose F is homotopic to F prime and F prime is homotopic to F double prime. We need to prove that F, no, I need to prove symmetry first, okay? So suppose F is homotopic to F prime. We need to prove that F prime is homotopic to F, okay? So since F is homotopic to F prime, there exists a continuous map big F from X cross I to Y such that big F of X comma 0 is equal to F of X and big F of X comma 1 is equal to F prime of X for all X in X, okay? Because we are given the fact that F is homotopic to F prime and big F is the corresponding homotopy. If big F is a homotopy from F to F, between F and F prime. Okay, so now we are defining this map G from X cross I to Y such that G of X comma T is equal to F of X comma 1 minus T. Since F is a continuous map from X cross I to Y, G is also a continuous map. Okay, and we also see that Gx comma 0 is equal to F of X comma 1, which is F prime of X, and G of X comma 1 is equal to F of X comma 0, which is small f of X, okay, from which it follows that the continuous map G from X cross I to Y is indeed a homotopy between F prime and F. This proves the symmetry of the underlying relation of homotopy. Now we have to prove transitivity. So suppose f is homotopic to f prime and f prime is homotopic to f double prime. We need to prove that f is homotopic to f double prime. Okay, since f is homotopic to f prime, there exists a homotopy between f and f prime. Let us denote that homotopy with big F, which is a continuous map from x cross I to y, and satisfying the following conditions: f of x comma 0 is small f of x, and f of x comma 1 is small f prime of x for all x in big X. Okay, and there is a homotopy between f prime and f double prime, which we denote by the continuous function f prime. Okay, from x cross I to y, such that the following conditions are met: f prime of x comma 0 is going to be equal to f prime of x, and f prime at x comma 1 is f double prime of x for all x in big X. Okay, good. Okay, now we define big G from the topological space x cross I to the topological space y by G of x comma t is equal to f of x comma 2t, where t belongs to this closed interval 0 to 1/2, and g of xt is equal to f prime of x comma 2t minus 1 when t belongs to 1/2 to 1. Okay. Okay, so this is how we define this function g. Now our claim is that g is a homotopy between f and f prime. Sorry, f between f and f double prime. Sorry, it will be from f to f double prime. Okay, so between f and f double prime. Okay, so the first thing to note here is that g is a well-defined continuous function by pasting lemma. So if you are not familiar with pasting lemma, go back to the chapter on continuous function from the same book by Moncrief. Okay. Let me state it if you don't remember it right away. So let me state this pasting lemma quickly. Pasting lemma. So if X is a topological space that can be written as union of two closed sets with A and B being closed in X, F from A to Y and F prime from B to Y are continuous, and also F and F prime agree with each other on the intersection of A and B. Okay, so if this is the situation, then one can construct a continuous function on the whole space using these two component functions. One can construct a continuous function h from x to y defined by hx is equal to f of x if x is in A and is equal to f prime of x if x is in B. So this is how you define this new function h constructed out of the two old continuous functions f and f prime. Okay, so this is the pasting lemma. We use this pasting lemma to construct the function g, to prove that the function that we defined earlier, big G, is indeed a well-defined continuous function. Because you see that in this case we have this topological space, right? X cross I, where I is this closed interval 0, 1. This is a topological space equipped with the subspace topology that it inherits from the real line. So it's equipped with subspace topology, and X is a topological space, given topological space, and X cross I is a topological space equipped with the product topology coming from the topology of X and the topology of 0, 1. Okay, so first thing to note is that 0, 1 half, this interval is closed here in 0, 1 in subspace topology. Okay, you can easily say that, since half 1 is open and hence 0, 1 half is closed in 0, 1. Okay, so this is closed in 0, 1, and X is both open and closed in the topological space X. So we can take X to be closed as well. So the product of these two closed sets is going to be a closed set in X cross I in product topology. So we see that X cross 0, 1 half is closed in X cross I. Similarly, X cross 1/2 1 is closed in X cross I in product topology. Okay. Okay. Now, now let me write down the definition of G again. So G was defined using this formula x comma 2t for t belonging to this interval, which is of course a closed interval in 0 comma 1, and gxt is defined as f prime of x comma 2t minus 1 for t belonging to 1/2 to 1, which is also a closed interval in 0 comma 1. Okay, so this function big F is a continuous map, right? Is a continuous map. In this case, we x cross 0 comma 1/2 to y, right? And f prime similarly is a continuous function from x cross 1/2 to y, where this and this are closed sets. They are both closed sets in x cross I, and we also immediately see that x cross 0 1/2 union x cross 1/2 1 is equal to x cross I. Okay, and also check that, so that the intersection of these two sets is the intersection of these two sets is x cross this singleton 1/2, right? And on this, these two functions f and f prime agree. It's easy to check, since f x okay, so you plug in 1/2 here, you get x comma 1, right? And you plug in 1/2 here to get f prime of x comma 0, right? 2 times 1/2 minus 1 is 0. And we know that f of x comma 1 is f prime of x, and we know that f prime at x comma 0 is also f prime of x, so that they are equal, which means that these two functions f and f prime agree on the intersection as well. Okay, so we satisfy all the requirements of pasting lemma, which means that the function g is a well-defined continuous function on X cross I, the union of these two constituent sets. Okay, all right, good. Now, okay, let me erase everything. And now, notice that okay, so I erase the definition. Gxt is f x comma 2t when t is from 0 to 1 half and is equal to f prime at x comma 2t minus 1 when t is between 1 half and 1. Okay, so also notice that gx comma 0, okay, so this formula holds because t is equal to 0 and 0 belongs to this interval. So this is fx comma 0, which is f of x, which follows from our previous discussion, and g of x comma 1 is equal to a big F prime of x comma 1. Okay, and big F prime of x comma 1 is going to be f double prime x. Okay, so what did we find? We found that g is a continuous function from x cross I to y, satisfying these two conditions, which means that G is a homotopy between F and F double prime. Okay, that is F sim F double prime. So this proves the transitivity of this relation, and hence this is an equivalence relation. Okay, QED. Okay, about the relation of path homotopy. Okay, so the proof is exactly the same of homotopy. So a few words about the transitivity, about checking the transitivity of the path homotopy. Okay. Um, so I just say quickly about the path homotopy of between two paths in the on the topological space X. X is a topological space, and say we have three paths, okay, which are continuous maps from I to big X. Okay. Um, I have to prove if F is path homotopic to F prime and F prime is path homotopic to F double prime, okay, then F is path homotopic to F double prime. So this is the transitivity property, okay, that needs to be satisfied if I need to prove that sim sub p, or the path homotopy, is an equivalence relation. Okay, so let us quickly check how we can do that. So for this, we try to draw a table um, we are given the fact that f is path homotopic to f prime, and we are also given the fact that f prime is path homotopic to f double prime. So let big F be a path homotopy between f and f prime. Okay. So which means that big F is a continuous function from I cross I to X, right? Such that the following conditions are met. Big F of S comma 0 is equal to small f of s, and big F of S comma 1 is equal to f prime of s. Also, big F of 0 comma t is the initial point x0 of the two paths, and big F at 1 comma t is the final point x1. Okay, so there are a few other things here, since these are maps from I to X, and since they are paths, we want the initial point of the three paths to be the same, right? We want f of 0 to be the same as f prime of 0 to be the same as f double prime of 0, which is equal to x0, the initial point. And for the final point, we want f of 1 to be equal to f prime of 1 to be equal to f double prime of 1 to be equal to x1, the final point in X. Okay, x0 and x1 are 2 points in the topological space X, big X. Okay, and these four equalities hold for all st in the closed interval I, in the interval I. Okay. Okay, so now for this situation where f prime is path homotopic to f double prime, let f prime be a path homotopy between these two paths, path homotopy, which means that big F prime is a continuous map from I cross I to X, such that following four equalities are satisfied. F prime at S comma 0 is f prime of s, and f prime at s comma 1 is going to be equal to f double prime of s, and the initial point is f prime 0 comma t, which is x0, and f prime 1 comma t is the final point x1. Okay, so these are the data we are given. Now let us construct this map G from I cross I to big X, defined in the following way. G of S comma t is equal to f of S comma 2t, okay, when t belongs to 0, 1 half, and GST is equal to f prime of s comma 2t minus 1 when t belongs to 1 half and 1, this closed interval. And the claim is that this map G from I cross I to X is a path homotopy between f prime and f double prime. You can easily check it. So we need to show that G of s comma 0 equal to f of s, and G of s comma 1 equal to f double prime of s, and we have to show that G of 0 comma 2 is x0 and G of 1 comma t is equal to x1. Okay, so that G is a continuous map from I cross I to X can be proved using pasting lemma as before. About these equalities, it is straightforward to check. So let me show you how to do that. So G of s comma 0, okay, see that if you plug in 0 here, then you're going to get fs comma 0. So this is equal to fs comma 0, okay, and from what we have here, fs comma 0 is small f of s. Okay, so this is proved, this is checked, and gs comma 1, see that from the definition you have to apply this formula since t is 1. So gs comma 1 is equal to fs comma, you plug in 1 here to get just 1, is fs comma 1, and fs comma 1 is f prime, sorry, yes, fs comma 1 is f prime of s, right? So gs comma 1 is equal to f prime of s. Well. What did we do? I think G okay, sorry, I made a mistake here in this formula. So gs comma 1 is equal to f prime s comma 1, okay, and f prime s comma 1 f prime s comma 1 is equal to f double prime of s. This way we prove that gs comma 1 is equal to f double prime of s. Okay, this is proved. Okay, so now I have to check these two equalities. Let us do them. I need some space. Okay. Okay, so let me erase apart from here. So now G0 comma T is, according to this definition, is equal to big F 0 comma 2t when t is in this interval, and is equal to f prime 0 comma 2t minus 1 when t is in this interval, right? 1/2 and 1. This follows from the definition of G. And this is nothing but equal to x0. Why? Because f of 0t equal to f prime of 0t is equal to x0 for all t in I. Okay. So taking these two equalities here, we see that g of 0t is identically equal to x0 for all t in I. Okay, so now g of 1 comma t, similarly using this definition, we see that this is equal to f of 1 comma 2t when t is in this interval, and f prime of 1 comma 2t minus 1 when t is in this interval. Okay, again we see that this guy is equal to g1t is simply equal to x1, since f1t equal to f prime 1t is equal to x1 for all t in I. Okay, good. So this way we check these two equalities, which proves that G is a path homotopy between the paths f and f prime, f and f double prime, sorry. G is a path homotopy between the two paths f and f double prime. This way you check the transitivity of uh, this relation, the relation of path homotopy. Okay, so the proof of um, uh, symmetry and reflexivity are exactly the same of homotopy. Okay, so we leave it to the readers or the audience. Okay, so now a quick example of homotopy. Example, we will close this segment with this example. Let f and g be any two continuous maps from a topological space X to R2. So it is easy to show that F and G are homotopic to each other. The map big F x comma t, defined as f of x t is 1 minus t times small f of x plus t times g of x. If we define this map f from x cross I to R2, so if we define this map f from x cross I to R2, then we say that f is clearly a continuous map from x cross I to R2 using the continuity of f and g, and we check that fx comma 0 is just small f of x, and fx comma 1 is g of x, which proves that indeed big F is a homotopy between these two continuous maps. Okay, I take a break here. So in the next segment, we are going to define product between between two paths. Okay, provided they follow certain conditions. All right. Thank you for attending the first segment.